Okay, we've talked about projections, different projection methods and families. When we're working with spatial data and research, there's really only a few projection methods that we use, and we typically use them within a projection system. So I'm going to cover some of those now. UTM is the one you will probably use the most. It's Universal Transverse Mercator. It was created to cover the entire Earth. They actually break the Earth up into 6-degree zones. Okay, and you'll hear the term zone, like we're in zone 10 north. You'll hear that a lot. That's zone 10. Here we are right there. Okay, there's Northern California, and Humboldt County is right in the middle of zone 10. In other words, if you're going to be working in different parts of the US, different parts of the world, you're going to use different zones within UTM. Again, UTM being Universal Transverse Mercator. Do you need to know that? Okay, so now this is if we look at geographic data, flattened out, which we'll talk about in a little bit. Okay, if we look at that as each zone, okay, so that there's not as much distortion, we break it up. You can again see here's UTM Zone 10 North, that's where we are, and it makes this little strip. But the strip is not really rectangular, even though you'll see it illustrated like this sometimes. That's with a lot of distortion at the poles. Take away that distortion and we end up with this little point, this little zone here, okay, and it is broken up into north and south, so it's kind of like an arrow or a triangle pointing north. When we zoom into just the US and look at it with a different projection, we can see that here is zone 10. Again, it's good for Northern California. Southern California, you'd want to be using zone 11. I worked in Colorado for a long time, so we use zone 13. And again, depending on where you are in the Earth, you may use a different zone. UTM coordinates are recorded using a northing, going north-south, and an easting. Now these are interesting coordinates because the northing is literally the number of meters you are from the equator. So where we are, it tends to be over 4 million because we're over 4 million meters from the equator. That's kind of cool, I think. So that's the northings will be around 4 million. The easting is different. There's no thing like the equator for us to measure from for each zone. So what they do is they take and they move the easting, it's called a false easting, they move it to the west 500,000 meters. So it's actually zero easting is actually outside of the UTM zone. And then they measure back to the east. Now the reason they did this was originally created by the US military, and they don't like negative numbers. It's really common for people to drop negative numbers and all of a sudden you'd be pointing your artillery pieces in the wrong direction. So the military doesn't like negatives, they got rid of it by moving zero out of the zone. So you will always see eastings, or almost always see eastings as positive numbers, and the middle of the zone will be somewhere around 500,000. Okay, for southern zones, you start at the South Pole measuring north, so it's different. Northern zones, we start at the equator and measure north. South Pole, or southern zones, we start from the South Pole and measure north. There is a confusion factor that I need to mention here because we usually talk about UTM Zone 10 North, but some folks will use UTM Zone 10N. Now, the problem there is that there are also regions. These little boxes are regions. And if you take a look, we're actually in region T, and region N is down here near the equator. Region N, sorry. So I always write UTM Zone 10 North to make sure that I'm being clear about that. And UTM Zone 10 South if I'm in the southern hemisphere, to make it separate from these regions. And that's what these are referred to. Okay, that is UTM, by far the most commonly used in research that I see. We'll talk about state plane, which it would be the next. And here's the actual math for it if you want to do that, but it's optional. Another important projection system to know is state plane. This is widely used in the United States for counties and for agencies. It uses different projection methods, either Lambert conformal conic or transverse Mercator, so similar to UTM. And what the United States did was they took each state and then they selected a projection method and settings based on the shape and the location of the state. And so California has a bunch of zones running north-south. Alaska, though, has a bunch running, north-south. Alaska runs east-west. Same thing in different parts of the country. So different states have different projections within each of these zones. You will hear folks talk about State Plane California Zone 1. That's actually ours in Humboldt County. I used to work in State Plane California Zone North. So some are north, central, and south, while others, especially the ones that have a lot of zones, like California, are numbered. And here's California. So California has zone 1, 2, 3, 4, 5, and 6. And they broke it up like this because they wanted to have smaller areas, and that will limit the amount of distortion within each zone. Also notice they followed the county boundaries. And again, the counties are still using State Plane quite a bit. So depending on which county you're in, you may find they're using a different zone. Also, one thing to know is NADITY 3 goes with one version of State Plane, which you'll see here has 6 zones. And then NAD 27 goes for a different one where there's actually 7. LA County used to have their own zone. Of course, 83 is later, but you may see either one. If you're working in LA County, you may be in zone 7. Now, we work with LA County. They've got very sophisticated GIS there, so I wouldn't be surprised if they've moved out of 27 into 83. So the origin for the State Plane systems is also moved toward the center of the zone. Again, that's to help with the size of the numbers. Here's the actual settings that go into the PRJ file, and if you have a shape file and you open the PRJ, these are the actual settings that you'll see. Won't go into that in too much detail right now. I do want to instead cover a couple other projections that you will see. State Plane and UTM are the ones we use by far the most commonly for research, unless you're working at a global scale. At global scale, things change. We can't use those. We have to use something global, and then we have to make some other decisions, different priorities. So orthographic is one you will see a fair bit because it's the one that comes up in Google Earth. It comes up when you look at a NASA photograph of the Earth, because this is kind of how the Earth would look if you're out in space. And a key question is to say, well, is this distorted? This is how it looks from space. Is it distorted? And the answer is, well, it's projected, so it's got to be distorted. In fact, if we go ahead and run it through Blue Spray, the distortion tool that you'll be using this week, you'll see that it actually is really distorted. Not so much where it's we're looking straight on, or the Earth is flat to us. Okay, here I've positioned North America towards us, but the area around it, and especially if we look at, here what's happening with these continents, they are getting squished. Okay, the U.S. looks fine, continental U.S., but these other continents really are heavily distorted, especially with area, right? They're just being smushed. So there's always distortion, even if it looks like what you've seen from space, what you might expect the Earth to look like. Webb Mercator is definitely one of the most extreme of this. This is another video where I show you the old Webb Mercator. I've left this up because you can't zoom all the way out with Webb Mercator anymore, but very highly distorted, and they don't allow us to zoom out anymore. And in fact, Google Maps has now gone to a spherical looking projection, orthographic projection, to get away from that. And hopefully the web will continue to improve. Another one that I just mentioned because it is really confusing to new GIS folks is this is geographic data. So it's spherical data, latitudes and longitudes, but it's been projected. In other words, it's on a flat surface. So again, this is distorted. Even though the data is latitude and longitude, which is inherently not distorted, we have now projected it. And by projecting it, we have now distorted it severely, right? Again, Antarctica does not look like this.